Reimer Tiemann reaction. Phenol reacts with chloroform and alkali base such as potassium hydroxide to give salicylaldehyde. The reaction was discovered by Carl Reimer and Ferdinand Tiemann, hence the name after them. So, before starting the reaction, let me tell you, in Reimer Tiemann reaction, the reactive intermediate formed is a carbene, which is very much important reactive intermediate. We will see what is the carbene. So, here we have phenol, which will react with CHCl3, that is chloroform, and KOH to give salicylaldehyde, that is ortho-hydroxybenzaldehyde. Here, this group, which we call as a formyl group, is getting attached to a aromatic ring. Hence, the reaction is also known as formylation reaction. Here is our reaction. Now, let's see the mechanism of the reaction. In mechanism, first chloroform and KOH reacts with each other to form a reactive intermediate, that is a carbene. So here we have chloroform, we have KOH. We all know KOH is basic in nature and base always finds an acidic proton. Proton of the chloroform is very much acidic because of the presence of three chlorines, three electronegative groups, hence get abstracted by the base, and with loss of water molecule we will be getting this anion, trichlorocarbanion, okay, which is being stabilized by K plus. So this type of salt is being formed in the reaction. And now in next step, chlorine leaves out with its 2 electrons, and minus of KCl gives us dichlorocarbene. So this carbene is very much reactive. Always remember, carbene are electrophilic, that means those are electron deficient species. Hence, carbenes are very much reactive. They are always eager to react with any species. Hence, any of the nucleophile when comes in contact with carbenes, they react with the carbene. That means carbene attack on that nucleophile to get electrons. So we have our phenol, which is a nucleophilic one. Okay, so this phenol would be treated with potassium hydroxide first to form a salt known as potassium phenoxide, because potassium phenoxide is more reactive than phenol itself as it has free electrons on the oxygen. So this potassium phenoxide will now work with carbene to give our desired product. So this potassium hydroxide, potassium phenoxide with dichlorocarbene. Okay, so here it attacks on the carbene and the bond opens at the Ortho position to oxygen double bond, and here are the rearranged bonds of the aromatic ring. Okay, you can see the aromaticity of the ring has been loosed here. Sorry, it is a negative charge. Aromaticity of the ring is loosed. So to retain the aromaticity, here is how minus of H plus works out, and here we are getting retained aromatic ring. Okay, O minus CHCl2. This step is known as rearomatization, that is retention of the aromatic character. Aromatic character is retained here. Now, with this species, another molecule of OH minus works here. So OH minus attacks on the carbon and cause one of the chlorine to leave out, giving such a species O minus carbon with H, OH and chlorine. Okay, so here again with minus of H plus, one carbon again leaves and there is a formation of carbon oxygen double bond that we call as a carbonyl group. So carbonyl group is being formed here with loss of HCl molecule. So here the ring has been formulated but till it is not the product, because here have we are with the salt, potassium salt, which we formed by treating phenol with KOH because of its reactivity. Now we have to get back our phenol by this salt. So we need to add acid. When the reaction is practically performed, this step is called as the acid workup. That means to uh, pull out the product in pure form, or to convert the salt into the product, that is the phenolic form. So here we are with our product, the orthohydroxybenzaldehyde, which we call as the salicylaldehyde, most important compound. Okay, so always remember this reaction works on only ortho formulation. Now you may have a question ki Baba, why only ortho formulation? Why not para? Here's the answer. So these are the two possible products of Reimer Tiemann reaction. One is the orthohydroxybenzaldehyde, that is salicylaldehyde, which we are getting, and one is the para product. Okay. In ortho product, you can see the phenolic hydrogen, that means hydrogen attached to oxygen, and the oxygen of a carbonyl, both are near to each other. This hydrogen is attached to one of the electronegative atom, hence it can form an electrostatic attractive bond between another electronegative atom, that is oxygen, and this type of bonding we call as hydrogen bonding. This hydrogen bonding is being formed here within the molecule. Both atoms are of the same molecule, hence call it as a intramolecular hydrogen bonding. Because of the intramolecular hydrogen bonding, compound becomes stable. This type of hydrogen bonding is not possible into the para product because hydrogen and oxygen are so much far away from each other. Hence, ortho product is more preferred, and hence Reimer Tiemann reaction always prefers ortho formulation. This is the thing we have to remember. Now the next reaction is Vilsmeier-Haack formylation. In this reaction, benzene or any aromatic compound reacts with dimethyl formamide and POCl3 to give benzaldehyde or corresponding aldehyde. The reaction was discovered by Anton Vilsmeier and Albrecht Barak. Okay, Vilsmeier-Haack formylation. So here is benzene with DMF, means dimethyl formamide, and POCl3. Okay, it is a product. Instead of benzene, if you would be using any aromatic compound like your aniline, anisole, phenol, you would be getting the corresponding aldehyde, corresponding aromatic aldehyde. So in mechanism, here we have first dimethyl formamide. Okay, and with that we are using phosphorus oxychloride, that is a POCl3. Always remember, phosphorus is most oxophilic compound. Oxophilic means uh, it has attraction to the oxygen loving one, so gets attacked by the oxygen, the P double bond O bond breaks and reforms, and chlorine gets away, and here we are getting the intermediate, which looks like this one, oxygen with a positive charge. Now the nitrogen, being neighbor one, will help oxygen to stabilize its positive charge by giving its own lone pair. So here is how it works. Yeah, so this is another intermediate, nitrogen with a positive charge. Now here the chlorine, which has been exhaled in the earlier step, will now comes into the picture in this step, will attack on the carbon and will cause the whole group to get out. Oxygen and phosphorus, the formation of pure double bond, is driving force for the reaction. So with loss of PO to Cl2, we are getting this species, which we will call iminium cation, because it is electron deficient species. Now guys, I have one question for you. You have to find out the name of PO to Cl2. If you will be unable, then the answer will be declared in my next video. So this iminium cation is now our electrophile, and this electrophile will react with the nucleophile, which is our benzene itself. So now we have benzene, that is the nucleophilic one. We have iminium cation, that is the electrophilic one. Both will work together, both will react with each other, and will give a neutral compound, that is a desired product. So here the nucleophile, that is the benzene, donates electrons to the electrophilic carbon and will form a carbon-carbon new bond. One may have question कि nitrogen has a positive charge and carbon is getting attacked. The reason I think you should know, which is the valency. Okay, so here again the ring has lost its aromaticity and it has to retain it. So the step follows, that is the re-aromatization with minus of H plus. The ring gets re-aromatized and here we are getting a compound. We can name it as N-dimethyl 1-chlorobenzylamine, we can call it. Okay, so now oxygen कहाँ से आएगा? Here is the important fact. Okay, sorry. The nitrogen will now give its lone pair and chlorine will leave out. So here is formation of imine bond, again carbon nitrogen double bond, and here nitrogen gets a positive charge, hydrogen. Okay, now the species has been electrophilic. We need another nucleophile which would be in the form of oxygen. Okay, so in this step we need to add water molecule in the reaction which works as a nucleophile. So now oxygen of the water molecule will attack on the carbon. The same, nitrogen has a positive charge and carbon is being attacked. So here we are getting H, OH2 plus and NaV2. Again, nitrogen being a neighbor will help oxygen by giving its lone pair, will get positive charge to itself, and we will get the species like H, OH and NaV2 plus H. Okay, so here with minus of H plus, dimethylamine gets exhaled and we will be getting our desired product with minus of H plus and minus of NHMe2, that is the dimethylamine. So here is the benzaldehyde which is our product of the Vilsmeier-Haack formylation reaction. Yep. So this H plus is taken by the chlorine which has been exhaled in the previous step. Yeah. Now for the sake of selectivity, you have to remember that if aromatic ring contains any of the substitution that shows an electron donating resonance effect, the groups such as OH, OR, NH2, NHR, NR2, etc. and etc. These groups are ortho and para-directing groups for electrophilic aromatic substitution reactions. This is what we have to remember, and for the sake of understanding, we are taking here two different examples. One is where we have taken phenol. Phenol is reacting with DMF-POCl3 and anisole is also getting reacted with DMF-POCl3. Now, firstly, I will write the possible products for both of the reactants. Obviously, OH and OCH3 both are the ortho para-directing. Hence, we would be getting ortho hydroxybenzaldehyde and para-hydroxybenzaldehyde in case of phenols. And in case of anisole, there again we will be getting two products: orthomethoxybenzaldehyde, which will look like this one, and another possibility is paramethoxybenzaldehyde. Okay, so out of these two products, which would be more stable, which would be more preferred? In case of orthohydroxybenzaldehyde, that is a product of phenol, this is looking like the product in Reimer Tiemann reaction. So here is again intramolecular hydrogen bonding, which makes the ortho product, or which makes the molecule more stable, and hence the ortho formulation will be more preferred on the phenol. So whether you are using Vilsmeier-Haack reagent or Reimer Tiemann Ortho formulation is more preferred. Now, in case of anisole or methoxyaldehydes, methyl hydrogens cannot undergo hydrogenation. Hydrogen bonding, and here the methyl group is somewhat bulkier group, and it may be sterically hindered when it is presence of large atom like oxygen, which is not the case in the para product. Both are far away from each other, hence no sterical hindrance, no crowding, and it makes this compound more stable. And due to the sterical hindrance, ortho compound is less stable, and hence the para product is more preferred in this case. Now, why methyl hydrogens do not undergo hydrogen bonding? Because the hydrogen which is attached to an electronegative atom can only suffer from electrostatic force of attraction, that is the hydrogen bonding with another electronegative atom near to it. This is what the thing you have to remember. Thanks for watching the video.